Hi everybody, this is Mrs. Peachy, your physical science teacher. And today what I'm going to be doing for you is a supplemental on ionic bonding for physical science. So we're just going to learn a little bit about how to look at certain ions and find out if they can bond together to make a compound, and then how to write those compounds out. And at the very end, I'm going to talk a little bit about some special ions called polyatomic ions that are a bit of an extension beyond the normal ionic bonding, but they're not too difficult to do if you just keep it simple. So we're going to try to keep it simple today. And I'm going to go ahead and show you what I have up down below here. And I'm going to give you the maximum screen so we really can see this. Okay, so here is my periodic table. And I like to have a periodic table that I keep all the time, that I can write on, and that I can put a lot of information on here. This one's lovely because it's laminated, so I can write on it and I can wipe off what I've written. I do write in whiteboard marker, dry erase marker, but if you write on this with Sharpie, as long as it's pretty durable, you can actually use a little rubbing alcohol and take it right off. And actually that's better because the Sharpie doesn't wipe off, whereas the, dry erase marker eventually rubs off pretty well. All right, so last time we talked, I showed you that each column has a number, and that columns 1 and 2 tell us that everything in this column has 1 valence electron. Everything in this column has 2 valence electrons. Everything in this column has 3, 4, 5, 6, 7, and 8. And that's important because remember that valence electrons are the ones found in the outermost shell of that particular atom. And those electrons are used in chemical bonding. So when we're looking at ionic bonds, we really have to pay attention to the valence electrons. The other thing we talked about is something called the Octet Rule. The Octet Rule, remember, says the maximum electrons in the valence shell is 8. Okay? 8 is the most stable configuration. 8 is great, we might say, if we're lame and like to use some fun rhymes to help remember stuff. So every atom is striving to have 8. And the only way it can do that is it's either going to get rid of electrons to get rid of that outer shell and go down to its next lower shell, or gain electrons. So atoms lose or gain electrons trying to get 8, right? So it's so stable that is the goal of each atom, even though, obviously they're atoms, they're not thinking, but we use words like that. All right, so for example, sodium. Okay, a little movie magic later, I can draw the electron shell diagram for sodium. 2 electrons in the first shell, 8 in the second shell, and 1 in that outer valence shell. Remember, 8 is great. The atom is going to either lose or gain electrons to get 8. It does whatever requires the least amount of energy. It's easier to get rid of 1 than it is to try to gain 7. So this is going to be given to something else. It's going to get rid of that. So when sodium gets rid of that electron, then that actually changes sodium's charge. Remember that in a stable, electrically stable element, that the protons should equal the electrons, right? But that's no longer true when that electron gets donated. So now it's going to have one fewer electron. Another way of saying that is it has one more proton. If it has one more proton, it has a positive 1 charge. Okay, so this is where we get the charges that are associated with each one of these elements. If it loses electrons, it gets a positive charge. If it gains electrons, it has a negative charge. And whether it loses or gains electrons depends on how many valence electrons it has. If it has between 1 and 3 valence electrons, that's supposed to be a V, sorry, it's going to lose. If it has 5 to 7 valence electrons, it's going to gain. If it has 8, it's lucky ducky, it's already stable. If it has 4, they can do both. That's what makes the atoms that are found in that group, that's the carbon group, so special. The atoms that are found in this group here, group 14, they can either lose or gain, so that makes them more capable of bonding with other elements. They have more of a variety of what they can do. So that's what makes carbon so fancy when it comes to being like the chemical or the element of living things. All right, so let's look at this then. Let's put some stuff on our periodic table to make it useful. Everything in column 1 is going to have 1 valence electron, so it loses that 1. So that means it has a positive 1 charge. In column 2, they have 2 valence electrons. They lose the 2, so that gives it a 2 plus charge, or positive 2 charge, and so on and so forth. We have 3 plus 3 charge. This can be plus or minus 4. And then we go the opposite way. Things in column 5 will gain 3 electrons. That's going to give it a negative 3 charge. Things in column 6 will gain 2 electrons, gives it a negative 2 charge, and things in column 7 will gain 1 electron, which gives it a negative 1 charge. So we don't exactly do the same thing that we did with the number of valence electrons. The charge depends on how many electrons it loses or gains. Again, this one has no charge because it is already great, because it is 8. All right, so then we can talk about making ionic compounds. Ionic compounds occur when a positively charged item sticks to a negatively charged item. They stick together much like the north pole of a magnet will stick to the south pole of a magnet, right? They are oppositely charged. Opposites attract. That's nothing new there. Now, we have to balance the charges. If something has 2 positives, it's going to have to balance to something that has 2 negatives. Otherwise, they don't cancel out. Sometimes you can have 2 positives balancing out to a single negative that has a negative 2 charge. So they balance. You have positive 2, negative 2. They're opposites, so they cancel each other out, okay? So that's what we got to look at when we're looking at our ionic bonds. Say we take the periodic table and we take something in the positive 1 column. Let's say sodium, because you guys are really familiar with this compound, okay? So sodium has a positive 1 charge. And if we take something with a negative 1 charge, say -1 is here. Say chlorine. Chlorine has a -1 charge. And so they balance. It's a 1-to-1 ratio, 1 sodium to every 1 chlorine. So we end up with a compound that's written sodium chloride, NaCl. So that's super easy. Well, sometimes it's not a 1-to-1 ratio. Sometimes it's a little different. Say we take sodium, +1, and we try to bond it to oxygen. Oxygen is -2. These don't match. In order to make these match, we have to add another sodium, because now we have a total of +2 and a total of -2. Okay, if we're adding down the columns. Now they match. So the way we write this compound out is Na2, because there's 2 of them, O. Notice we never put the 1 subscript. Okay? It's assumed that if there's no subscript, it means 1. Na2O. Sodium oxide. Okay? Now, you can do it the other way too. You could have magnesium, which is a +2 charge. And chlorine, which is a -1 charge, right? And they're not going to match. So you add an extra chlorine. Again, add down the columns. And you end up with magnesium and 2 chlorines, magnesium chloride. The charge never makes its way down here, guys. Okay? The charge doesn't make its way down here. It is how many of them. It stands for how many of them there are. Okay? So the last thing I want to show you, and I know we're almost out of time, is I want to show you polyatomic ions. See if I can get this up on the screen here. Okay, so polyatomic ions, you can see them right here. There's a whole bunch of them like this. Polyatomic ions are groups of atoms that together have a charge. So for example, we can look at the ion nitrite with an ITE at the end, and it's NO2, and that whole group has a -1 charge. Okay? Now if I want to go back to what I was doing before, if I have something nitrite that is NO2 with a -1 charge like that, I can bond that to something with a +1 charge. Say, for example, sodium again. So you have 1 sodium for every 1 nitrite. So this would be written NaNO2, sodium nitrite. Okay? Let's say instead of sodium, we used magnesium. Then we would need 2 of these nitrites in order to balance. And that would be written magnesium nitrite with a subscript of 2. So that's a little more complicated. These are the polyatomic ions. I said I would briefly cover them, and I'm not going to cover them much more because I don't want that to be too much information. Okay, so that is the end of your tutorial, on ionic bonding. If you have any more questions or concerns or would like me to go through some more practice problems with you, feel free to give me a call at extension 2204, or you can send me a webmail message. Hopefully that made a little sense, and I will talk a little bit later about covalent bonding. Have a great day.